Welcome to the Holographic Universe. This is part 1 of a 5-part workshop series designed to examine how quantum physics and recent scientific experiments are radically changing our understanding of life, our reality, and our spirituality. For example, in January of 2012, scientists at the GEO 600 gravitational wave detector in Germany announced they now had scientific evidence that the entire universe is a holographic projection around the Earth. We'll take a look at that claim in detail later in this workshop. But first, imagine, if you can, living at a time when everyone thought the Earth was flat, and we based our opinions, beliefs, judgments, and fears on that one single incorrect premise. Imagine believing that if you sailed too far west from Portugal, you'd fall off the edge of the Earth, and how that limited human lives and experience. When we found out the Earth was round, we had to make some serious adjustments in our thinking. But unfortunately, you're going to find out in this workshop series that we simply traded one set of limiting beliefs for another. Well, we're at a turning point in history once again, and I want to share with you this revolutionary idea that we are living in a holographic universe, and explore what that will mean in our everyday lives. Which brings up the question, who am I? And what are my qualifications to present this workshop? Well, my name is Stephen Davis, and that's all you really need to know, because I am not the one who will be speaking to you today. Although you will be hearing my voice, you will not be listening to my beliefs or my opinions, because I am not an expert in quantum physics. Instead, I have brought with me the real experts to talk to you through video clips and audio files and quotes from their books. I want you to hear all of this directly from them, the experts. And if you disagree with something you hear, you'll have to argue with them, not me. I'm literally just the messenger. My job is simply to bring you the message that the Earth is round, and give you the scientific evidence for it. What you do with that information is entirely up to you. For example, in 1991, Michael Talbot wrote a book called The Holographic Universe. Unfortunately, Michael died in 1992, just a year later. So this book is already 20 years out of date. And there's been a lot that's happened during that time in this field. But still, it's one of the best books I know to get started, and you'll be hearing a lot of quotes from it today. You'll also be hearing quotes from The Field by Lynn McTaggart, another excellent basic introduction to the subject. And you'll be meeting and hearing from a lot of different experts, mainly physics professors at various colleges and universities from all over the world, such as David Bohm, renowned quantum physicist at Princeton University; Carl Pribram, neurophysiologist, Georgetown University; David Albert, director of Philosophical Foundations of Physics, Columbia University; Richard Feynman, professor of theoretical physics, California Institute of Technology; John Hagelin, physics professor at Maharishi University; Stuart Hameroff, associate director of the Center for Consciousness, University of Arizona; Nick Herbert, assistant professor of physics, Monmouth College; Michael Ledwith, professor of systematic theology, Maynooth College in Ireland; Andrew Newberg, director of the Center for Spirituality and the Neurosciences, University of Pennsylvania; Dean Radin, professor, Saybrook Graduate School; Jeffrey Satinover, teaching fellow in physics, Yale University; Leonard Susskind, professor of theoretical physics, Stanford University; William Tiller, professor emeritus, Stanford University; Fred Allen Wolf, author of Taking the Quantum Leap and Parallel Universes; Brian Greene, professor of theoretical physics, Columbia University; and many, many more. But I want to introduce you first to Dr. Amit Goswami. Dr. Goswami is Professor Emeritus in Theoretical Physics at the University of Oregon, Senior Scholar in Residence at the Institute of Noetic Sciences, and author of 9 books on quantum physics, including The Self-Aware Universe and Science and Spirituality, A Quantum Integration. Listen carefully to what Dr. Goswami has to say.
This is the only radical thinking that you need to do. But it is so radical, it's so difficult, because our tendency is that the world is already out there, independent of my experience. It is not. Quantum physics has been so clear about it.
This is the only radical thinking that you need to do. But it is so radical, it's so difficult, because our tendency is that the world is already out there, independent of my experience. It is not. Quantum physics has been so clear about it. You'll be hearing that quote probably half a dozen times over the course of these workshops, and each time you hear it, it will make more and more sense. But now, let's begin by taking a trip into outer space, and then back into inner space, with a video called The Powers of 10. Pay particular attention to what outer space and inner space look like.
The picnic near the lakeside in Chicago was the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now every 10 seconds we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1 million meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the Sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The two little satellite galaxies of our own are the clouds of Magellan, 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus, so massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding.
You can see that outer space and inner space look very much alike. Lots of empty space. This video was made in 1977. As technology improved, scientists kept going deeper and deeper, and they found smaller and smaller particles and more empty space.
We were all taught in school that the world is made of stuff, of matter, of mass, of atoms. Atoms make up molecules, molecules make up materials, and everything is made of that. But atoms actually are mostly empty. For example, if this ball were the nucleus of an atom, a proton in a hydrogen atom, for example, then the electron circling this, which would describe the outer limits of that atom, would be out by that mountain over there, roughly 20 miles away. And everything in between is empty. In fact, the universe is mostly empty.
Within all the atoms and molecules, all the space within the particles take up an insignificant amount of the volume of it.
Dr. William Tiller said, within all the atoms and molecules, all the space within them, the particles take up an insignificant amount of the volume of an atom. But it's the particles that supposedly make up matter, so scientists focus on them in their experiments. And as the research continued, scientists discovered that the very small particles they were finding did not behave as they were supposed to. Basically, Newtonian physics only worked well on large objects, objects we can see with our naked eyes, but not on a subatomic level. This was the beginning of quantum physics, and the most famous experiment that got everyone opening their minds to new possibilities about the universe and how it works is called the double-slit experiment. Here is a cartoon that explains what happened in that experiment. Meet Captain Quantum.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment.
The first people who did these experiments, and these experiments of, crude experiments of this kind, were first performed almost 50 years ago, or more, 60 years ago. Those people were flabbergasted.
To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like waves.
Let's make sure we understand this double-slit experiment so far. When we shoot matter, like a BB or a marble, at a barrier with two slits, we get two bright streaks on the screen behind in line with the slits, like this. And when we shoot waves, like waves of water, through a barrier with two slits, one wave becomes two waves on the other side of the barrier, and when the two waves hit, they interfere with each other. If the top of one wave aligns with the top of another wave, it's called constructive interference, and the result is a new and bigger wave. But if the top of one wave aligns with the bottom of another wave, it's called destructive interference, and the result is that they cancel each other out and there's no wave at all. And when constructive and destructive interference happen together, you get an interference pattern on the back screen that looks like this. Now, if we shoot an electron, which we have always thought of as a particle, a little piece of matter, through a barrier with two slits, you would think we would get a pattern on the back screen that particles make, like this. But we don't. Instead, we get an interference pattern that waves make, like this. The conclusion is that electrons, which are the building blocks of what we call reality, are not solid particles at all, but exist as waves as well. In this wave form, they are called quanta, which is why the study of how they behave is called quantum physics. But that's not the end of the double-slit experiment. Let's rejoin Captain Quantum where he left off.
The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like waves. Physicists were completely baffled by this, so they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched.
So the electron is very peculiar. The electron is very peculiar in the sense that when you are not looking, electron can be here, can be there, or can be over there in the corner of this room. It can be all over this room, so to speak. But whenever we look, this is the strange thing about these electrons. Whenever we look, we always find them to be in one particular Geiger counter, although we may have a room full of Geiger counters. We never hear the Geiger counter sticking all over the room. This is the fundamentally important stuff about the electrons.
It was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Particles aren't really what they seem to be. They're momentary manifestations, momentary poppings of this deeper imaginary realm, this wave-like realm, this implicate order, as David Bohm would say it, this quantum wavy function, as quantum physicists might talk about it, in which there is no particle. There's just this waviness which can spontaneously pop out as particles.
Once again, let's make sure we understand, because this is so important. As we said earlier, when we shoot an electron toward a barrier with two slits without watching what it does at the barrier, we get an interference pattern like this. But when we watch or measure what happens at the barrier, the electron becomes a particle again and makes a particle pattern on the screen behind, like this. In physics, this is called the measurement problem, because the nature of an electron changes when you look at it or try to measure it. It collapses from being a wave into a particle in a specific location in space and time, which is what we see as reality. This is called collapsing the wave function. Remember that term, collapsing the wave function, because we'll talk more about it later. This means that an electron, the core element of what we call our solid physical reality, is only a solid particle, is only matter when someone is looking at it. Otherwise, it's a wave and not solid at all. In his book, The Holographic Universe, Michael Talbot said, "There is compelling evidence that the only time quanta, or electrons, ever manifest as particles is when we are looking at them. When an electron isn't being looked at, it is always a wave." To put it the other way around, the natural state of an electron is as a wave. It only pops out of its wave state to form a particle in a specific location in space and time when it is being observed. Then, when it's not being observed, it goes back into its wave state. But it turns out that it's not just the electrons that pop in and out of existence. Listen to Dr. Jeffrey Satinover.
Matter is not what we have long thought it to be. To the scientist, matter has always been thought of as sort of the ultimate in that which is static and predictable. We like to think of space as empty and matter as solid. But in fact, there is essentially nothing to matter whatsoever. It's completely insubstantial. Take a look at an atom. We think of it as a kind of hard ball. Then we say, oh, well, no, not really. It's this little tiny point of really dense matter right at the center, surrounded by a kind of fluffy probability cloud of electrons popping in and out of existence. But then it turns out that that's not even right. Even the nucleus, which we think of as so dense, pops in and out of existence just as readily as the electrons do.
Dr. Satinover said, even the nucleus of an atom, which we think of as so dense, pops in and out of existence just as readily as the electrons do. So it is not only the electrons that exist as waves and then pop into a specific location in space and time when they are observed, but also the nucleus. And the most recent research has even found that whole atoms and molecules do the same thing. Physicist Nick Herbert says this means that the world behind our back, where we are not looking and cannot observe, is always a radically ambiguous and ceaselessly flowing quantum soup. But whenever we turn around and try to see the soup, our glance instantly freezes it and turns it back into reality. Herbert believes this makes us all a little like Midas, the legendary king who never knew the feel of silk or the caress of a human hand, because everything he touched turned to gold. Likewise, we can never really know the true nature of the quantum universe because every time we try to observe it, it turns into matter. Richard Feynman, a physics professor at the California Institute of Technology, is reported to have said that if you really understand this double-slit experiment, you can understand all of quantum physics. You will hear me say fairly often that one of the best clues or hints about how our universe actually works can be found in our kids' video games. Right now, take a short look at a game called Minecraft.
Oh man, here we go, people. Minecraft, let's play. Oh, I can't believe I've never done this before. This game is the sweetest game, man. Oh, it is so awesome. Well, I'm so excited to get started, guys. I hope you're going to enjoy the series as much as I'm going to enjoy playing it. And today, we're just going to set up for the first night. We're going to try and make sure that we find a good little pad. Oh, God. I think I broke something. We're going to look for a nice place to start up and, ooh. Oh, God. Oh, God. Oh, God. This is not perfect, guys. This is absolutely perfect for a house. I'm going to build my house right into the side of this mountain. And when we come out of the house, we're going to come out with this amazing view of what can only be described as a rainforest. You know what I'm saying? Oh, my God, this is so awesome. This is perfect. Yeah, I think I'm... Oh, yes, this is perfect. Wait, is there a tree above me? Oh, my God, the sun is going down. The sun be going down.
Notice that when the player passes an object or turns in a new direction, whatever he had been looking at before disappears. Where does it go? Take a quick look again, and then we'll talk a lot more about that later.
Oh, man. Here we go, people. Minecraft, let's play. Oh, I can't believe I've never done this before. This game is the sweetest game, man. Oh, it is so awesome. Well, I'm so excited to get started, guys. I hope you're going to enjoy the series as much as I'm going to enjoy playing it.
Basically, unless the player is looking at something in the video game, it doesn't exist. It disappears, only to pop back up later if the player looks at it again. This is how quantum physics is telling us that our reality works as well. It means that our reality is not as real as we have always thought it was. Instead, as you hear many quantum physicists say, it pops in and out of existence. So, if matter is not solid and reality is not real, what is this physical universe that we experience and think of as so solid, that looks and feels so real to us? Two models have been developed to answer that question. One is the field, and the other is the holographic universe. When we speak of an electron existing as a wave, it isn't like an ocean wave or a radio wave. It is more like a wave of possible locations where the electron could end up as a particle when it is observed. It's a wave of possibilities. This wave of possibilities in which the quantum world exists has been called many names over the years, such as the quantum wave function, the implicate order, which was David Bohm's term, the Planck scale, named after Dr. Max Planck. These scientists like to name things after themselves, apparently. The zero-point field, named, of course, after Dr. Zero Point. The superstring field, the unified field. Mainly, it is just called the field. It is a field of unlimited possibilities out of which everything is created. Lynn McTaggart, author of The Field, defines it as a field of all possibility. In other words, everything you can think of, and everything you can't think of, and everything no one has thought of yet, already exists in wave form in the field.
Progress in our understanding of the universe through physics over the past quarter century has been exploring deeper levels of natural law, from the macroscopic to the microscopic, from the molecular to the atomic to the nuclear to subnuclear levels of nature's functioning, so-called electroweak unified scale, grand unified scale, super unified scale. And what we've discovered at the core basis of the universe, the foundation of the universe, is this single universal field of intelligence, a field which unites gravity with electromagnetism, light, with radioactivity, with the nuclear force, so that all the forces of nature and all the so-called particles of nature, quarks, leptons, protons, neutrons, are now understood to be just different ripples on a single ocean of existence. That's called the unified field or superstring field, a single universal field of intelligence, an ocean of existence at the basis of everything, mind and matter. And all the so-called particles of the universe, the forces in our universe, everything in the universe are just ripples on that ocean of existence. That's the unified field. And that field is a non-material field. Planets, trees, people, animals, we're all just waves of vibration of this underlying unified superstring field. We're really living in a thought universe, a conceptual universe. Quantum mechanics is just the play and display of potentiality. So the point I'm making is the deeper you go in the structure of natural law, the less material, the less inert, the less dead the universe is, the more alive, the more conscious the universe becomes. Then when you get to the foundation of the universe, the unified field or superstring field, it's simply a field of pure intelligence. Intelligence because it's the fountainhead of all the laws of nature, all the fundamental forces, all the fundamental particles, all the laws governing life at every level of the universe have their unified source in the unified field. That makes the unified field the most concentrated field of intelligence in nature. Non-material, dynamic intelligence. Those are the properties of the unified field. So, as you said, the tighter physics have tried to grasp onto physical reality, to understand what it's really made of. What are the core building blocks of life? At the basis of it all, life, the universe, slips through your fingers. And you come up with something that's increasingly abstract to come to the realm of pure abstraction. And that's what the unified field is. It's pure abstract potential, which rises in waves of vibration to give rise to the particles, the people, everything we see in the vast universe.
So the field is a place outside of space and time where everything, all possibilities, already exists, but only in wave form. This field does not contain particles. It is not matter. It is not part of the physical universe. Instead, it is what the entire universe is made from these waves of possibilities.
Physicists give this a name. They call it our quantum wave function because it seems wavy. However, this wave function isn't just a wave of matter like an ocean wave or a sound wave or any kind of wave of matter. It's a wave of possibility. It's a kind of thought wave. And because it is a wave of thought or possibility or not matter, it's invisible to us. But we can't explain what we do see as matter in these small corners of space and time unless we picture that these matter particles somehow come out from or emerge from these thought wave patterns which are invisible to us.
Quantum mechanics is really the play and display of information, the play and display of potentiality, waves of information, waves of potential electron. And it's important, the word potential. This isn't the world of electrons, it's the world of potential electrons. But when you have to ask the question, waves of what, really? What is the field that is waving? Is it the ocean? No, it's a universal ocean, an ocean of pure potentiality, an ocean of abstract potential existence. We call it the unified field, or superstring field. And that's what we're made of.
Fred Alan Wolf said something very important. We can't explain what we do see as matter unless we picture that these matter particles somehow come out from or emerge from these thought wave patterns. The problem is that no one can prove that the field exists. You can't see it, you can't photograph it, you can't measure it, you can't hold it in your hand. But when quantum physicists assume the field is there, they can make incredibly accurate mathematical predictions about the physical universe and how it behaves, which they cannot do without assuming the field is there. Think of it like electricity. You can't see electricity itself. You can only see what electricity produces, the light it makes and the power and the other effects we count on every day. And when we see those effects, we know that electricity must exist. The same thing is true for the field. Even though we can't prove it exists, nothing makes sense without it, in light of the results of the most recent scientific experiments. Think about taking a radio into the outback of Australia. I can imagine that the Aborigines would stare at that little box for a while, trying to figure out how the music came out of it. They might even tear it apart, looking for very little people inside playing very small instruments. But eventually they would deduce that there must be radio waves in the air that they couldn't see and couldn't prove existed, that this little box could receive and translate into sounds they could hear. That's what we're dealing with when it comes to the field. We can't see it, we can't prove it, but we know from looking at the effects that the field must exist. But how did this field come into being? Who made it? Where did it come from? Why is it there? Science has no answer for these questions. They only know that the field must exist. So I will not talk now about how the field was created, or who might have created it, or how it already contains all possibilities, because I want to stick only to the science right now in this presentation. We will have to leave that discussion for another time. The next question we can ask, though, is how is reality created from the field? Most quantum physicists agree that it is a very similar process to the creation of a hologram. In other words, the universe we see is a holographic universe.
When we look at some of the modern scientific views of reality that have tried to get down to the nitty-gritty, we see that at its ultimate level, say in M theory or string theory, that reality is not solid, it's mostly empty space, and whatever solidity it has seems more to resemble a hologram picture rather than material, harsh, solid reality.
So to understand the holographic universe, we have to understand what a hologram is and how it is created. The simple definition, according to Michael Talbot in the Holographic Universe, is that a hologram is a virtual image, an image that appears to be where it is not. In other words, a hologram is an image that is not real. The technical definition from the Merriam-Webster Dictionary is that a hologram is a three-dimensional image reproduced from a two-dimensional pattern of interference produced by a split coherent beam of radiation, as a laser. Don't panic. I'm going to explain that technical definition very simply. Let's look at how a hologram is made. It is actually a two-step process. First, we shoot a laser beam out of a laser gun, and then we immediately split that laser beam into two beams. One of the beams, called the reference beam, makes its way and eventually hits a sensitive holographic plate or film. This is like the film we used to have in our cameras before digital photography. The other half of the laser beam hits an object first, in this case an apple, and then hits the holographic plate. When these two parts of the original laser beam come back together at the holographic plate, they interfere with each other, just like the waves did in our double-slit experiment, and they form an interference pattern on the holographic plate. If you look at the holographic plate at this point, you cannot see the apple. All you can see is the interference pattern, which looks like a bunch of waves. This is step 1 of creating a hologram. Remember those 3D pictures that were such a fad in the 90s, which looked just like a bunch of meaningless waves? But if you refocused your eyes, an image would pop out for you to see. So, for our hologram, we now need a step 2 to see the image of the apple. In step 2, we focus another laser beam on the holographic plate where our apple sits in wave form, and if we get just the right angle, out pops the apple, looking very real and very solid.
You might wonder what I'm holding in my hands here. Looks like a black picture, but if I shine a light on it at a certain angle, watch what happens. It's a picture, it's a hologram. Now this isn't one of those cheapskate holograms, this is the real deal. Watch what happens when I turn it. We have genuine three-dimensionality there, okay? There's no denying that. In fact, one of the things that the camera doesn't really pick up is that the image actually comes right out of the picture to the human eye. I mean, if I place my finger here, in terms of my depth perception, that's as if I'm touching its nose, and yet I can move that far back into it. There's nothing there, and yet it appears to be that I could literally actually stroke it. There's no denying that there's real three-dimensionality there. This is a particularly good one because it's got these big gnashers, and if I try to move it a little closer to get you a real good look inside the mouth here, you can see very, very clearly, if you look at the teeth in relation to the tongue behind it, there's genuine movement here. You are actually getting to see behind things. Yeah, so that's the wonders of the hologram. And yet there it is. It's in a completely two-dimensional space. It doesn't really exist, even though my eyes tell me that it does exist.
I'd like you to see a few examples of just how far we've come in our holographic technology over the past few years, and how real holograms that we produce today are beginning to look. The first example is from 2007. It is part of an international conference being held by the company called Cisco. The man on the left is at the conference center in Bangalore, India. The two men on the right are on stage in India as holograms, but they are actually in San Jose, California.
So at this time, I'd like to beam up Martin De Beers and Chuck Stuckey back from San Jose. Martin, I'm beaming you up now with my spatial controls. How are you doing? Hey, Chuck, how you doing?
John, we're doing great, thank you.
Hey, John. Hey, guys. Yesterday, Martin, you looked a little bit bigger than me. I hope today we're going to play with some sizes and we'll kind of give the audience an idea how we can make variations on that.
I believe so, John. I'll tell you, it's been a long day here in California. We were up here at 3 a.m. our time. We're still wearing the same shirts. And we had a 5.6 magnitude earthquake about an hour ago. So I'm here to tell you, though, that everything's fine. We've had no major damage here in San Jose. And, as a global company, we'll continue to operate.
Well, it's amazing. You can see each other as though we were playing poker. I can see you sweat a little bit. I can see that you both shaved since the last time I saw you. But we don't have the sense of smell yet. But it is...
that was a good thing, John.
In the holographic universe, Michael Talbot said, "It is relatively easy to understand this idea of holism in something that is external to us, like an apple in a hologram. What makes this difficult is that we are not looking at the hologram, we are part of the hologram." The two men on the right can touch each other, and they look very real to each other. That's because they are part of the hologram. But if the man on the left went over to where the other two men are standing, he could pass his hand through them and feel nothing. That's because he's outside the hologram. Remember that. It's a very important point. It was easy to tell who was a hologram and who wasn't in that example from Cisco. But now watch something produced just 3 years later, an advertisement for something called the DVE room.
This is the DVE Immersion Room. It just won the Global Telepresence Video Conferencing Product of the Year Award. And what I'm about to experience, so I've been told, absolutely has to be seen to be believed. The DVE Immersion Room takes video conferencing to a whole new level. And I must say, I'm already very impressed with this luxury boardroom environment.
Hi, Sarah. I'm David, your immersion room tour guide.
This is amazing. You're in 3D. Hi.
Hi. I am glad that we could get together this way via real telepresence. That's what you're experiencing, real telepresence. It's the best way for people to connect around the world, and it's truly a revolutionary way for people to collaborate.
This is beyond my experience. It looks like you're right here.
Right, I am. I'm right here via real telepresence. It's over a high bandwidth network connection. Here, let me show you. This is a 9-foot wide, volumetric 3D image that appears over the boardroom table. This will take your presentations to a whole new level. And that's just one example. This is the most realistic telepresence system ever developed. And it's also an advanced simulation environment for business, education, scientific research, and defense.
So where are you exactly?
Well, I am in Irvine, California. But anyone can connect in this personal way to anywhere else in the world. I mean, it's virtually limitless. London, New York, Tokyo, you name the city, and we can make telepresence happen there.
I can easily see leaders of corporations, diplomats, even heads of state in the immersion room. It breaks down the barrier of distance, like we're all here in the same room.
Exactly.
Today, holograms are being used in the most creative of ways, in music concerts. First, there was Carrie Underwood as a hologram joining Brad Paisley on stage to do a duet.
We keep saying that we're okay. I don't want to settle for good, and I pray I miss the way that it felt back then. I want to feel that way again. Been so long that you forget the way I used to kiss your neck. So on fire, so in love, way back when we couldn't get enough.
Then Snoop Dogg and Dr. Dre brought Tupac Shakur back to life via hologram on stage in a concert in Coachella.
Hey, it's Snoop Dogg performing with Tupac at Coachella this... Wait a second! Tupac's still alive? Yeah! You know what this is? Nope! Very confused right now.
Dr. Dre and Snoop Dogg performed at Coachella last night with Tupac Shakur.
What the is up, Coachella? But how is this possible? Tupac died in '96. This defies everything we know as human beings.
Well, it was a hologram of Tupac.
Okay, yes, it's a hologram. Tupac is still dead. But this was freaking amazing! Behold the resurrection of Tupac!
He comes like rising up from the bottom of the stage.
And then you'll never guess what happened! No! He's been shot by a hologram of Biggie! Or they just turned off the hologram machine.
It was so cool.
It was very cool!
Apparently, plans are in the works to do the same with Elvis, although he never really died, of course. And now they're talking about bringing Marilyn Monroe back for a live concert via hologram. Michael Talbot said, "Creating the illusion that things are located where they are not is the quintessential feature of a hologram. If you look at a hologram, it seems to have extension in space. But if you pass your hand through it, you will find there is nothing there. Despite what your senses tell you, no instrument will pick up any energy or substance where the hologram appears to be hovering. This is because a hologram is a virtual image, an image that appears to be where it is not." So here's the point. Many highly respected quantum physicists are telling us, based on the latest research, that we are living in a hologram, that our reality is a virtual image, an illusion, that it isn't real. University of London physicist David Bohm, for example, believes that despite its apparent solidity, the universe is at heart a phantasm, a gigantic and splendidly detailed hologram. Dr. Jacob D. Bekenstein, professor of theoretical physics at the Hebrew University of Jerusalem, said, "An astonishing theory called the holographic principle holds that the universe is like a hologram. The physics of black holes, immensely dense concentrations of mass, provides a hint that that principle might be true." There is a famous TV program on the Discovery Channel called Nova, and in November of 2011, they broadcast a show called The Fabric of the Cosmos, What is Space? It was hosted by Brian Greene, theoretical physicist and professor of physics at Columbia University, who wrote the book called The Fabric of the Cosmos. Here is a 5-minute video clip from that program.
As we examine the fabric of the cosmos ever more closely, we may well find far more surprises than anyone ever imagined. Take me, for example. I seem real enough, don't I? Well, yes. But surprising new clues are emerging that everything, you and I and even space itself, may actually be kind of hologram. That is, everything we see and experience, everything we call our familiar three-dimensional reality, may be a projection of information that's stored on a thin, distant, two-dimensional surface. Sort of the way the information for this hologram is stored on this thin piece of plastic. Now, holograms are something we're all familiar with, from the security symbol you find on most credit cards. But the universe is a hologram? That's one of the most drastic revisions to our picture of space and reality ever proposed. And the evidence for it comes from some of the strangest realms of space, black holes.
This is a real disconnect, and it's very hard to get your head around. Modern ideas coming from black holes tell us that reality is two-dimensional, that the three-dimensional world, the full-bodied three-dimensional world, is a kind of image of a hologram on the boundary of the region of space.
This is a very strange thing. When I was a younger physicist, I would have thought any physicist who said that was absolutely crazy.
Here's a way to think about this. Imagine I took my wallet and threw it into a black hole, what would happen? We used to think that since nothing, not even light, can escape the immense gravity of a black hole, my wallet would be lost forever. But it now seems that may not be the whole story. Recently, scientists exploring the math describing black holes made a curious discovery. Even as my wallet disappears into the black hole, a copy of all the information it contains seems to get smeared out and stored on the surface of the black hole, in much the same way that information is stored in a computer. So, in the end, my wallet exists in two places. There's a three-dimensional version that's lost forever inside the black hole, and a two-dimensional version that remains on the surface as information.
The information content of all the stuff that fell into that black hole can be expressed entirely in terms of just the outside of the black hole. The idea then is that you can capture what's going on inside the black hole by referring only to the outside.
And in theory, I could use the information on the outside of the black hole to reconstruct my wallet. And here's the truly mind-blowing part. Space within a black hole plays by the same rules as space outside a black hole or anywhere else. So, if an object inside a black hole can be described by information on the black hole surface, then it might be that everything in the universe, from galaxies and stars to you and me, even space itself, is just a projection of information stored on some distant, two-dimensional surface that surrounds us. In other words, what we experience as reality may be something like a hologram.
Is the three-dimensional world an illusion in the same sense that a hologram is an illusion? Perhaps. I'm inclined to think yes, that the three-dimensional world is a kind of illusion, and that the ultimate precise reality is the two-dimensional reality at the surface of the universe.
This idea is so new that physicists are still struggling to understand it. But if it's right, just as Newton and Einstein completely changed our picture of space, we may be on the verge of an even more dramatic revolution.
And now listen to Leonard Susskind, professor of theoretical physics at Stanford University.
But there's a quote that I like. Very much. It comes from a famous intellectual by the name of Sherlock Holmes. And it says, when you have eliminated all that is impossible, which, by the way, sometimes takes 5 years, when you have eliminated all that is impossible, whatever remains must be the truth, no matter how improbable. The thing I'm going to tell you tonight is one of those things which seems nutty, it seems wildly improbable, but it wasn't just something that some of us, I wasn't alone in saying this, that some of us just said, oh, one day, maybe the world is a hologram. That's not the way it happened. The way it happened was exactly this way. When you eliminate everything that's impossible, whatever is left over must be the truth. So let me tell you a little bit about where we're going. Good. Okay. What is this thing which Sherlock Holmes might have eventually concluded after trying everything else? And the answer is that in a certain sense, in a certain peculiar sense, the world is a hologram. Now, not everybody knows what a hologram is here. You know, you've all seen these pictures which look three-dimensional. They're made out of a film, which is a flat piece of film. Nevertheless, they look fully three-dimensional. I'll tell you eventually what a hologram is. But the idea that the world is a hologram is a wild idea, or at least a seemingly wild idea. That is what we now believe, and there's an enormous amount of very, very sharp mathematical evidence for this picture. It's not something that was just made up for fun, the world is a hologram, or a black hole is a hologram. There is very sharp mathematics to it. I'm not going to do the sharp mathematics. This is the universe, or at least this is somebody's representation of the universe. And what I'm going to tell you next is it's not just black holes which are holograms, but in a certain sense the entire universe can be represented as a hologram. Or any finite region of the universe, any big chunk of the universe, can be represented as a hologram.
So now let's come back to that press release we started with. Scientific evidence that the entire universe is a holographic projection around the Earth. Here's what it said specifically. German scientists have been trying to understand why their equipment that measures gravitational waves has been picking up a particular sound. One possible answer that they've come up with is that the entire universe is a holographic illusion. For many months, the GEO 600 team members had been scratching their heads over inexplicable noise that is plaguing their giant detector. Then, out of the blue, a researcher approached them with an explanation. In fact, he had even predicted the noise before he knew they were detecting it. According to Craig Hogan, a physicist at the Fermilab Particle Physics Lab in Batavia, Illinois, GEO 600 has stumbled upon the fundamental limit of space-time, the point where space-time stops behaving like the smooth continuum Einstein described and instead dissolves into grains, just as a newspaper photograph dissolves into dots as you zoom in. It looks like GEO 600 is being buffeted by the microscopic quantum convulsions of space-time, says Hogan. If this doesn't blow your socks off, then Hogan, who has just been appointed director of Fermilab's Center for Particle Astrophysics, has an even bigger shock in store. If the GEO 600 result is what I suspect it is, then we are all living in a giant cosmic hologram. The idea that we live in a hologram probably sounds absurd, but it is a natural extension of our best understanding of black holes, and something with a pretty firm theoretical footing. It has also been surprisingly helpful for physicists wrestling with theories of how the universe works at its most fundamental level. So we're going to end part 1 of this workshop with 2 last examples of holograms that demonstrate how we could have been living in a hologram all along and not been aware of it. The first example is from the movie The 13th Floor. Here's the setup. A German scientist has built a machine that creates a hologram that a human being can go into and be part of. So far, he is the only one who has actually gone into the hologram. But he gets killed, and his partner and friend, named Douglas Hall, wants to find out who killed him. The scientist left a clue to his murder inside the hologram of Los Angeles, California in 1937. So Douglas Hall is going into the hologram for the first time to try to find the clue. Pay particular attention to Douglas Hall's reaction when he realizes he's inside the hologram for the first time.
Set the timer for 120 minutes.
Set it for 60, it's better.
120 minutes, Whit.
60 is safer, I'm setting it at 60.
Whit. 1, 2, 0.
120 minutes. Engage timer. Preparing user for download into simulation. Program link ready for download.
This is Grierson 117, West Winston, Pasadena. Bridge
Transference beginning. Download complete.
Excuse me?
You owe me $12.05. Listen, young man, I do not have all day.
Ferguson, anything wrong? John, are you okay? Terribly sorry, ma'am. Someone will be right with you. John?
Yeah.
Cigarette?
No, thanks. Don't smoke.
Since when? Listen, John, why don't you break for lunch? Get some fresh air. You look terrible.
You look pretty good.
Let me remind you of what Michael Talbot said. It is relatively easy to understand this idea of holism in something that is external to us, like an apple in a hologram. What makes this difficult is that we are not looking at the hologram, we are part of the hologram. Maybe you recognize this. The last example of a hologram comes from the TV series Star Trek: The Next Generation. If you're not a Trekkie, the Starship Enterprise traveled around the universe 24/7, 365. So there was no time or place for the crew to take a break or a vacation. Instead, they had something on board called the holodeck, where any hologram could be created for you to enjoy in your free time. In this episode, Commander Riker is testing out some new improvements to the holodeck and wants to play some jazz in New Orleans.
Computer, I'd like some place to play some music, a little atmosphere.
Specify.
Jazz,
Era.
circa 1958.
Location.
Kansas City. No. New Orleans, Bourbon Street Bar, New Orleans. Around 2 a.m.
Program complete. Enter when ready.
Very good. Very good indeed. Now I'll need someone to play with. A trio. Piano, bass, and drums, and a bone for me. Now an audience. Whoa, too many. I was thinking of something a little more intimate. Great job, boys. But computer, blondes and jazz seldom go together. Now that is truly exceptional. But more sultry. Gentlemen, if this is what you call enhancement, you've got a gift for understatement. What's your name? Tell me you love jazz.
My name is Minuet, and I love all jazz, except Dixieland.
Why not Dixieland?
You can't dance to it.
My girl. What's a knockout like you doing in a computer-generated gin joint like this?
Waiting for you.
Waiting for me? You can't be serious.
Oh, yes, Will. I've never been more serious in my life.
I'm going to have to leave for a while to see to my duties.
Your work's very important to you.
It is me. It's what I am.
Can we dance once before you leave?
Sure, why not? How did you learn to dance so well?
From following you. I can anticipate your lead. So, tell me about your work. What is it about it that consumes and enthralls you?
An interesting choice of words. That's exactly what it does.
You're very fortunate
I know that.
to be exactly where you want to be. And it's great that you realize it.
I'd be a fool not to realize how lucky I am to be on this ship serving with these people. It's like a dream come true. Just like this.
A dream? Is that what this is? Is that what I am?
I know you're a computer-generated image, but your smell, your touch, the way you feel, even the things you say and think seem so real.
Thank you.
How far can this relationship go? I mean, how real are you?
As real as you need me to be.
The conclusion to part 1 of this workshop is that quantum physics is very clear. What we call reality is actually a holographic picture that only looks and feels real to us inside it. Now maybe this will have more meaning for you.
This is the only radical thinking that you need to do. But it is so radical, it's so difficult, because our tendency is that the world is already out there, independent of my experience. It is not. Quantum physics has been so clear about it.
One last quote from Michael Talbot in the Holographic Universe. There is evidence to suggest that our world and everything in it, from snowflakes to maple trees to falling stars and spinning electrons, are only ghostly images, projections from a level of reality so beyond our own that it is literally beyond both space and time.
If you want to see fear in a quantum physicist's eyes, just mention the words, the measurement problem. The measurement problem is this: an atom only appears in a particular place if you measure it. In other words, an atom is spread out all over the place until a conscious observer decides to look at it. So the act of measurement or observation creates the entire universe.
Millions and millions of blobs of energy and light, photons and electrons. They make up this imaginary three-dimensional solid world, which doesn't exist at all according to relativity or quantum mechanics.
I hope now you can see how this idea that we live in a holographic universe is like learning that the Earth is round and not flat. It is going to change everything we think and believe. So if all of this is true, and quantum physics says it is, the next logical question is, so what? So what if the world we see is a hologram? What are the consequences of this? And how does this affect my daily life? I can give you a one-word answer right now: profoundly. But we're going to take a closer look at the answers to those questions in the next 4 parts of this workshop. Your homework, what I want you to do in preparation to watch part 2 of this workshop series, is first, watch the entire movie called The 13th Floor, and secondly, practice seeing the world around you as a hologram that isn't real. It often helps to look at everything around you as a movie set, with you as an actor in the movie. In part 2, we'll continue our look at the holographic universe with the question, exactly how is this holographic universe created for us to experience as physical reality? Once you have done your homework, please visit www.holographicuniverseworkshops.com for more information about continuing with part 2 of this workshop series. In the meantime, you can download my free ebook, Butterflies Are Free to Fly, A New and Radical Approach to Spiritual Evolution, by visiting www.butterfliesfree.com.